Hello there, I'm Borna and I'm your organic chemistry tutor. Today I'm here to show you how to balance a redox reaction on an organic compound. Let's get to the board. Alright, so this is the reaction we're going to be dealing with. This is an oxidative cleavage of an alkene with permanganate in an acidic environment to give two carboxylic acids, and we're going to learn two methods to balance this equation. The first method is going to be the method of half reactions. So half reactions. The goal of this method is to break the reaction down to an oxidation half reaction and a reduction half reaction and make sure that the number of electrons produced and consumed is basically the same. So obviously MnO4 minus and Mn2 plus are involved in a half reaction. So let me highlight that using purple. So these are going to be two of the species that are involved in a half reaction because the element manganese is at the center of this half reaction, and then the other one is going to revolve around our organic compound. So I'm going to highlight that as well. So let's first focus on our MnO4 half reaction, and we need to discover whether it's a reduction or an oxidation. Okay, so we need to determine the oxidation state of manganese to be able to figure that out. It's obvious it is +2 here because it's an ion, no problem. This is a little more complicated, so the method that I'm going to use is that the oxidation state of manganese plus the oxidation state of the oxygens, which is going to be -2, is going to be equal to the charge of the species. So that means that X, which is the oxidation state of manganese, is going to be +7, meaning that manganese goes from +7 to +2, meaning that it's being reduced, meaning that it is basically gaining 5 electrons. So this is our reduction half reaction. And it also means that MnO4 minus is an oxidant in this process. Now let me erase the oxidation state calculations because we don't need that anymore. Now I want to make sure that the charge on the left side of the reaction is equal to the charge on the right side of the reaction. Now how am I going to do that? In acidic conditions, we can use H pluses to balance the charge. Under basic conditions, we have to use OH minuses. So the charge on the right side of the reaction as it stands is +2. The charge on the left side of the reaction is -6. So I'm going to add 8 H pluses to bring the charge of the left side of the reaction to +2 as well. Also, doing that leads to hydrogen not being in balance on the right side of the reaction. So I'm going to add 4 water molecules to balance the hydrogens. And basically the last thing that I want to do is that I want to make sure that the balance of the oxygen atoms the oxygen atoms are in balance. And they actually are, because I have 4 oxygen atoms on this side and we have 4 oxygen atoms on that side, and that totally does make sense. So no problem there. So this is our reduction half reaction. So let me write that down up top. So this is my reduction half reaction. So that is easy. Now, as for the oxidation half reaction, we have an alkene. That is going to 2 carboxylic acids. Now this is a little more complicated because one species is going to more than one on the right, but that doesn't matter. So what matters is how many electrons the one species on the left consumes or produces. Now, first of all, let me tell you that this alkyl group, which is right here, and this methyl group that is right here, they don't undergo any change in oxidation state. So we're only going to focus on the atoms that actually do undergo a change in oxidation state, which is going to be this one, which ends up here, and this one, which ends up here. Alright, so for this molecule, I'm going to use a slightly different method to calculate the oxidation state of the blue carbon and the green carbon. So this carbon is expected to have 4 electrons, okay? It has 1 electron from this carbon-carbon bond, so I'm going to write 1 electron here. It has 2 electrons from these carbon-carbon bonds for oxidation state purposes. And just to be clear, you assign the electrons in a bond to the more electronegative party to that bond. And for carbon-carbon bonds, or bonds between the elements of the same kind, the electrons are going to be split evenly. And then for the carbon-hydrogen bond, the electrons go to carbon, so it has 2 electrons from that bond as well. It is supposed to have 4. It has 5, so the oxidation state of that carbon seems to be -1. So I'm just going to erase my calculation, assign the oxidation state of -1 to that carbon, just be done with it. And then yellow, that can remain in place. The oxidation state of the green carbon is -1 here. And then I can do the same analysis for the blue carbon. It is supposed to have 4 electrons. It has 2 from the bond with the green carbon. It has 1 from the bond with the purple carbon, and it has 2 from the bond with hydrogen. So it has 5. So the oxidation state of that also is -1. And then in the carboxylic acids, the carbon doesn't take any of the electrons from the carbon-oxygen bonds, so those belong to oxygen, and then takes 1 from the carbon-carbon bond. So it is supposed to have 4. It has a 1, so the oxidation state is +3. Same thing with this carbon. So the blue carbon and the green carbon go from being -1 to being +3. And that means that they have increased in oxidation state, and that means that they have released electrons. Now, as I said, the number of electrons per 1 molecule of reducing agent is what matters. And that is going to be 8 electrons per molecule of reducing agent, because each one of those carbons go from -1 to +3, so that is going to be 4 released electrons per atom. Alright, so that is that. Let's erase the oxidation state calculations so we can balance the equation properly. The next thing that I want to do is that I want to take care of the charge. There, so that is going to take care of the charge. Now, as for the hydrogen, since there is like a lot of hydrogens on the right and on the left, I'm just going to disregard that for now. I'm going to worry about the oxygens, and then I'm going to check that the reaction is imbalanced by counting the hydrogens. Okay, so there is 4 oxygens on the right. There is none on the left, so it means that there is none on the left, so it means that I have to add 4 water molecules. And as for the number of hydrogens, the the yellow piece and the purple piece, they're not touched, so we don't have to really worry about that. The blue carbon goes from having 1 hydrogen to having 1 OH, so no change in hydrogen there. Same thing with the green carbon. So the only change in hydrogens is a result of the introduction of H pluses. So 4 H2Os, hydrogens are in balance. Perfect. So now we have the oxidation reaction, we have the reduction reaction. How are we going to actually balance the equation? Now let me write the reduction half reaction. Okay, so what we want to do is to basically multiply the top reaction by 5. So 5 times 4 H2Os plus our alkene going to this carboxylic acid plus, and just for simplicity, how about I just call this PR for propyl and methyl there. So then we have a PR, and then we have that plus 8 electrons plus 8 H pluses, and then multiply the oxidation half reaction by 8, and then what that is going to do for me is that is going to ascertain that the number of electrons reduced and the number of electrons consumed is going to be the same. Alright, so let's do the multiplication. So I'm going to use a different color. So for the top row, there is going to be 20 H2Os plus 5 of my alkene going to 5 the first carboxylic acid, 5 acetic acids, plus 40 electrons plus 40 H pluses. For the second row, there is going to be, and I'm going to use green for that, there is going to be 64 H pluses. There is going to be 8 MnO4 minuses. There is going to be 40 electrons. There is going to be 8 Mn. 2 pluses, and there is going to be 32 H2Os. Alright, so all I have to do now is to add these two together. It may seem a little complicated, but it's really not that bad. Okay, so the electrons are going to cancel out, and that's what matters. So that's good. And then let's see. So we have 20 H2Os here. We have 32 on the other side, so I'm going to say we have 12 and then totally forget about that. So this is taken care of. We don't need to worry about it anymore. As for the H pluses, we have 40 there, we have 24 here, so I'm going to totally forget about this. And then I'm going to say that we have 24 here. And that seems to be working. Alright, great. So let's add these two. So I'm going to have 24 H pluses plus 5 of my alkene plus 8 MnO4 minuses going to 8 Mn2 pluses. My handwriting is not the best, I'm sorry about that. Plus 12 H2Os. Alright, so that seems to be the balanced equation. So let's just make sure that certain elements are in balance, and once that is taken care of, we can be sure that we did it right. So manganese is in balance. We have 8 manganese atoms on the left, 8 on the right, so not a problem there. As for the carbons are also in balance, so not a problem there. Let's see what the oxygens are like. So on the left, we have 32 oxygens. On the right, we have 10 plus 10 plus 12, so that is also in balance. As for the hydrogens, we have okay, so we said that the number of hydrogens in this and the number of hydrogens in these two is going to be the same. So I'm not going to worry about those two. As we said before, I'm just going to worry about the rest of the things that have hydrogen. So there's 24 H pluses on the left, and then there's 24 H plus, there's 24 hydrogens on the right. So hydrogens are also in balance. So great. So this reaction is in balance. Perfect. Now, I'm going to teach you another method to use to balance this this reaction. Let's go talk about that. So this method is a little less laborious. It's easier to do. So we have our alkene, and then that goes to Mn2 plus, that goes to butyric acid, and that goes to acetic acid. And let me just give myself some space to add the reaction coefficients. Okay, great. So the oxidation state of manganese and MnO4 minus is +7. That is going to +2, so that is a change of gaining 5 electrons. Alright. And then we have 2 atoms that undergo a change in oxidation state. Let me just use different colors to demonstrate that. In the other molecule. And as we said, they go from an oxidation state of -1 to +3. And as I said before, it doesn't matter that one species on the left gives rise to 2 species on the right. That's totally fine. Like, the only thing we need to know is the number of electrons in total that that molecule gains or loses. So it goes from -1 to +3 in this and +3 in that. So in total, it's basically releasing 8 electrons. So all I have to do is to multiply that by 8 and multiply this by 5. So let's do that. So I'm going to give 8 to this, and I'm going to give 5 to that, and this is going to ascertain that basically the number of electrons traded is going to be balanced. So I'm going to erase the analysis of the oxidation states so we have more space, because we don't need this anymore. Okay, you're done with this. Alright, now we want to worry about the charge, and the charge I'm going to balance with H pluses. So on the left it appears that we have a charge of -8, and then on the right we have a charge of +16. So if I add 24 H pluses to the left, that is going to take care of the charge, because 24 minus 8, that is going to be 16, or +16, and then we have a charge of +16 on the right. That adds up perfectly. Not a problem there. And then finally we need to worry about the oxygens. And then as for the oxygens, we have 32 oxygens on the left, and then we have 20 oxygens. So I'm going to add 12 H2Os to take care of the oxygen, and then if the hydrogens are in balance, we should be good. And indeed they are in balance, because we have 24 hydrogens here. As we said, the number of hydrogens in this and this are the same, no need to worry about it. And then there's 24 hydrogens here, so we're good. So 2 methods for balancing an oxidation reduction reaction containing organic molecules. If you like this video, don't forget to like, share, and subscribe, and do the things that people do when they like a video. And did I say subscribe? Yes, I did. See you next time.